All right. Hello, ladies and gentlemen. I thought I would do a video of the review questions 9 to 15 from the 7.6 review. So let's just get right on to that. Question number 9. A proton of mass of 1.67 times 10 to the negative 27 traveling with a speed of 1 times 10 to the 7 meters per second collides with a helium nucleus at rest. The proton then rebounds with a speed of 6 times 10 to the 6 meters per second, while the helium nucleus moves forward with a speed of 4 times 10 to the 6 meters per second. What is the total momentum before? All right, so we've got a small object, we have a large object. This has at rest, and this is traveling quite quickly. So total momentum, P is equal to mv. So we would have m1v1 plus an m2v2. And the mass of the proton being 1.67 times 10 to the negative 27 kilograms. And it's traveling at 1 times 10 to the 7 meters per second, plus 0. We don't know what the mass is. In fact, that's the last question, but we know the velocity is equal to 0, so the momentum is equal to 0. So 1.67, 10 to the negative 27 times 1 10 to the 7, and that's equal to 1.67. 1.67 times 10 to the negative 20 kilograms meter per second. What is the momentum of the proton afterwards? Well, P is equal to mv. The mass of the proton is 1.67 times 10 to the negative 27. The velocity of the proton is negative 6.0 times 10 to the 6 meters per second. Using my Casio FX 260 Solar. And we go away, and we get, oh, come on, where'd my pen go? Here we go. And we get a momentum, these are vectors, come on, of 1.0 times 10 to the negative 20 kilogram meters per second. But this is a negative value, and that's important to recognize this because this is a vector, because we had the proton coming in, and then the proton is bouncing out. And so we have a direction that is going to be positive, which means the opposite direction is going to be negative. Hence, we have this negative sign here. Okay? And that even corresponds with the book. Funny that. What is the momentum of the nucleus afterwards? Well, so here we have, let's deal with this way, momentum of the proton plus momentum, no, let's, I'm doing things differently, I don't want to do things differently. So we have P before is equal to P after. Okay, so we know that the momentum, so we have the momentum of the proton plus the momentum of the nucleus before. And that's equal to the momentum of the proton plus the momentum of the nucleus after. Let's call those primes. We know the momentum of the nucleus before is equal to 0, so all of the momentum was in the momentum of the proton. So that was a negative. So that was 1.6. So that was 1.67 times 10 to the negative 20 kilograms meters per second. And then we have the momentum of the proton, and that was a negative 1.0 times 10 to the negative 20 kilograms meters per second. And then we have the momentum of the neutron, or the nucleus. So this is where you can see that it's really important to have this as a negative sign and recognize it's a negative, because now we're going to add this to both sides. And so the momentum of the nucleus after the prime, that's what we're finding, is 1.67 plus 1, so that's equal to 2.67 times 10 to the negative 20 kilogram meters per second. And then, what is the mass of the nucleus? All right, so we know that the momentum of the nucleus is equal to 2.67 times 10 to the negative 20 kilogram meters per second. That's equal to mass times velocity. So that's, that's equal to our mass. And we're told that the velocity, well, the nucleus moves forward with a speed of 4.0 times 10 to the 6 meters per second. So our mass then will be our 2.67 times 10 to the negative 20 divided by our 4.0 times 10 to the 6 meters per second. So 2.67, 10 to the negative 20 divided by 4, 10 to the 6 equals 6.68 times 10 to the negative 27 kilograms. Now, it doesn't ask you to do this, but if we take this number and we divide it by 1.67 times 10 to the negative 27, we get a value of 3.997. We get a value of 4. A helium nucleus is 4 times the mass of a proton. And the helium nucleus has a 2 plus charge, has a mass that is equal to 4. And this is where the whole idea of neutrons came in, because the charge can be easily quantified. And the idea that the mass was so much greater that said, hold on, there must be something neutral that has this. So we take a look at the atomic mass of helium and see the value of 4. All right, just a bit of extra, no extra charge. A stationary flat car of 4 times 10 to the 4th kilograms is rammed by a locomotive of 6 times 10 to the 4th kilograms at 4.5 meters per second. What is the velocity if they stick together? So we've got our locomotive. Yeah, I know, it's an old-time locomotive. And it's got a capture in the front. And then we've got our flat car. And this is coming in, then bang. It's supposed to be a B. And then they stick together. We want to know their velocity. All right. So, I mean, this really comes down to our conservation of momentum. M1v1 plus an M2v2 is equal to, and then they stick together, so that's where we would say M1 plus M2 times V. So we have our stationary car, 4 times 10 to the 4 times 0 plus 6 times 10 to the 4 times 4.5 is equal to, then the masses of 4 times 10 to the 4 plus 6 times 10 to the 4 times our velocity. So right away you can see this goes to 0. And you have 6 10 to the 4 times 4.5. That's 2.70 times 10 to the 245. And so this will be 4 10 to the 4 plus 6 10 to the 4. That's equal to 245. Yeah. 1.0 times 10 to the 5 times our velocity. So 2.7 10 to the 5th divided by 1 10 to the 5th, we get a value of 2.7. You can almost do that in my head. So momentum is conserved. Here the momentum was just in the one car as of, it's traveling at 4.5 meters per second. And when they're combined together, the velocity is slower. It just makes sense. Same momentum. All right. 2.5 kilogram cars are moving at 2 meters per second. These are, so these are carts. Can't put cart there. What is the momentum before the spring pushes them apart? So these are, okay, if you remember, back when we actually used to go to school, we had those carts. We have wheels here, and we had a wheel here in the middle, and they had like hoops on the top and the bottom. We'd send them down, and sometimes some of them they would have a thing in the front, and there was a spring, and this could move in. And so what we do is that we take two of these carts and we stick them together, and the spring is pushing them apart, but we've got a little pin that keeps us from, you pull the pin and then they fly off in opposite directions. Except what we have in this case is that we have the two carts, they're tied together, and so they are moving, and then bang, the two carts separate, and we know one travels off at 3 meters per second. Great. So two are moving at 2 meters per second, and the front cart moves at 3. What was the momentum before? That's what we want to know. So P is equal to mv. So our m is 2.5 plus 2.5, and our velocity was 2. So 2.5 plus 2.5 is 5 times 2, so that's equal to 10 kilogram meters per second. Excuse me. So far, so good. What was the momentum of the front car afterwards? Well, the momentum, they're just asking for mv, so that's equal to 2.5. It's just the one cart, and it's now traveling at 3 meters per second. And so that's equal to 7.5 kilogram meters per second. All right. What was the velocity of the second cart afterwards? All right, so here we have the idea of the momentum being conserved. So we have P before equaling P after. So beforehand, we know the momentum is equal to 10 kilogram meters per second. And then we have our m1v1 prime plus our m2v2 prime. And so this is 2.5 kilograms times our, let's call it v1 prime. And then we have our other 2.5 kilograms times our 3.0 meters per second. So we know that this is 7.5 kilogram meters per second. This is 2.5 v1 prime plus, and this is equal to 10 kilogram meters per second. So we are going to add negative 7.5 to both sides. And so that would give us 2.5 kilogram meters per second on this side is equal to 2.5 times v1 prime. We're going to divide both sides by 2.5. And so v1 prime is equal to 1.0 meters per second. So if we go back up, no, okay, we can't go back up, so let's just redraw our question. So we have then our card here, we have our first card here. This one is traveling at 3 meters per second, and this one's traveling at 1 meter per second. And they were both traveling in the positive direction, forward direction. What velocity would the front car have if the second car became stationary? So after the bang, after the prompt, or we have two cars going on, and this one is now going off with a velocity, but here the velocity is equal to 0. So again, P before is equal to P before is equal to P after. P before is 10 kilogram meters per second. And then we have our M1 B1 prime plus our M2 B2 prime. But now we're saying this one is equal to 0. So this is now 10 kilogram meters per second. And this one is 2.5 kilograms times our B2 prime. So we'll have 10 divided by 2.5, and so B2 prime is equal to 4.0 meters per second. So the spring was such, if the conservation momentum things worked out, so that this one came to 0 velocity, this one would be traveling at 4 meters per second away rather than 3 meters per second. Just sort of a what-if type of question. And yeah, there are things such as conservation of energy that come into allowing a situation like this happen. Question number 12. So we've got a truck. And the truck is traveling at 0.8 meters per second. And what we have is we have a brick, and there's a string tied on here, and what's happening is we're bringing in some scissors. We're going to cut the string, dropping this onto here. So we have, momentum before is equal to momentum afterwards. So if we talk about M1 B1 plus our M2 B2, that's going to be, well, they're combined afterwards. We can say M1 plus M2 times B. Now, our M1, so let's say it's our 1.5 kilogram brick, and it's traveling at 0 meters per second because it's being dropped. And then we have our 2.5 kilogram toy truck moving at 0.8 meters per second. And that's going to equal our M1 plus our M2. So that's 1.5 plus our 2.5 times our velocity. Well, 1.5 times 0, I can do that one in my head. That's equal to 0. And then we have 2.5 times 0.8. Let's try it again. 2.5 times 0.8. And that's equal to 2 kilogram meters per second. And we have 1.5 and 2.5, and so that would be equal to 4.0 times our B. And so we'll have B is 2 divided by 4, and that's equal to 0.50 meters per second. So together they'll be traveling at half a meter per second. All right, the Marooned Astronaut. Okay, I was just looking at the answers, and they have an answer for 13, which is a numerical value, but then they don't have 14, which has a numerical value. So the Marooned Astronaut. So we are, this is the space shuttle, and so we've got our doors open, and here's our payload bay. Here's our second door open, and here's our Canada arm there, and we've got entrance there and stuff like this. And so now what we've got is we've got our astronaut. And our astronaut is floating out in space, and he's lost his jetpack power, and he looks gorky. Trying to draw. So what does it say that he's got? Explain how an astronaut who is stranded in free space a short distance from a spacecraft might employ his knowledge of momentum to return safely to the craft. Why must he be very careful about momentum? Okay, so let's give him a big camera or something here. Let's try this again. Let's make And so he's floating out in space, and he's got this big camera here, and here's the spacecraft, and he has to get back over to there so he can go into the hatch and get back inside and be safe, right? And he's got to put the engines on there. Anyways, so what he can do is that if he takes the camera and he throws it in this way, because this is a question where we have m1 plus m2 with a velocity hopefully equal to 0, and then we have an m1 v1 prime plus an m2 v2 prime. If he throws the camera in that direction with a certain momentum, then he's going to have an equal and opposite momentum that way. The faster he throws this, the faster he'll move back, but if he throws it that way, then he'll be moving towards the spacecraft, hopefully. But he's got to be careful. Like, okay, what happened is that the end of his spacecraft became detached from this. Like, they always go out there with tethers. They're going to make sure that they don't get loose. This is a bad situation. It's bad. You never want to be there. Just, okay, a story. Prior to the space shuttle, there was a project called the Gemini project. And in the Gemini project, what they did is it was a two-man, Gemini mean two, and they had this spacecraft, and they had these doors that would open up. And it was one of the first times that they were doing spacewalks. The Russians had done spacewalks and so on, and the Americans were going to do it. A lot of the work that they did with the Gemini was leading up to the Apollo, so that they could go to the moon. But so you had this situation. So, anyways, what happened was that you had these hatches that would open, these car doors that would open, and the one astronaut went outside, and he was floating around and stuff like that, and then tried to get inside. But the way his like as soon as if you take a balloon and you put a little bit of air into it, but then you put it inside and remove all the air pressure from inside, then the balloon expands. It gets larger and larger and larger. And so there was air pressure inside the spacesuit, but when they opened up the hatch and he went out, he ballooned up like a balloon. And for him, it was extremely difficult for him to get back into the spacecraft. And it was a very panic situation. I was reading that the second guy who was inside the hatch actually had been given orders that he might have to cut this guy loose, because they would both be dead if he couldn't get him back in. but they pushed and pushed and shoved and shoved and shoved and pushed and shoved, and eventually were able to get him back in. But it was a scary, scary situation. And there was like a liter or more of liquid in the bottom of his spacesuit at the end of it. A lot of it sweat. Yeah, most of it probably would have been sweat, but bad, bad situation. Anyways, no reason, no momentum, just me talking. Anyways, a 2 kilogram bullet is traveling at 500 meters per second. I've reworded the question, but that's really what's happening. And lodges in a sandbag and cart system of 4.5 kilograms. So what have we got here? Well, we've got our gun, and as I said, there's our 22 long, and we're shooting this, and we've got a sandbag, and a sandbag is just a target that is part of the cart. And so as the bullet comes flying through here, it lodges inside the sandbag. It's an inelastic collision that allows it to travel. So here, so the gun really doesn't come into this question at all. All the gun has done is to give the bullet the velocity. What we're more concerned about is this second bang, as it were, when the bullet becomes becomes lodged in the sandbag into the cart system and causes this to move off. So what have we got here? So this is an M1V1 plus an M2B2 question, and that's not it. And so then we can say, well, that's going to equal, they're lodged together, so this would be an M1 plus an M2 times a V. So the velocity, the momentum of the bullets, left-hand side here. So that's 0.002 kilograms times 500 meters per second plus 0, starting off at 0. Then afterwards, we're going to have 0.002 kilograms plus 4.5 kilograms times our velocity. And you can sort of see right now that the mass of the bullet is really inconsequential to the mass of the full system, but it does give it the momentum. So 0.002 times 500, so that's equal to 1 kilogram meter per second. So this will be 4.502 times V. So 1 divided by 4.502, that's a velocity then of 0.22 meters per second. That's how fast the cart and bullet. Now, if we took our 1 kilogram meter per second divided by 4.5, we get 0.22. Like, the mass of this is inconsequential to the conservation of momentum. Finally, we've got two kids. We've got one wagon here. Maybe these are scooter boards in the gymnasium. Okay, we've got another scooter board here, and we've got Billy, and Billy's got a rope, and we got Johnny, and Johnny's got the other end of the rope, and they're pulling. And so let's say this is our 45 kilogram, this is our 60 kilogram, and he begins pulling, and when he's pulling, now their velocity is equal to 2 meters per second. So really, how do we calculate this? Well, we have something before and we have something afterwards. And so our momentum before is our M1V1 plus our M2B2. And afterwards, we're going to have our M1V1 prime plus our M2B2 prime. Well, here the velocity is equal to 0, so that's 0. Here the velocity is equal to 0, that's 0. So 0 is equal to our M1V1 prime plus our M2B2 prime. So let's put in those values. 0 is equal to 45. He gets a velocity of 2 plus a 60, and he gets a velocity of v2 prime. So this is going to be 2 times 45 is 90, comes over to the other side. We get negative 90 is equal to 60 V2 prime. And so then we have V2 prime is equal to negative 90 over 60. That's equal to negative 1.5 meters per second. Negative sign? Well, it's going back towards the other direction. The 45 kilogram boy is going forwards, and we'll say that's positive, so that becomes a negative velocity. And there we go. That's how fast he's moving back. All right, there you go, ladies and gentlemen. 30 minutes just over. Have a great weekend. I will not be online this Friday. We are doing something for the grads. It's a long weekend, so we'll talk to you on Tuesday. And as I say, Tuesday I'll have a worksheet review. I think it's just good for this momentum stuff. It helps solidify help solidify the ideas and concepts. All right, take care. Bye-bye.